So, welcome back to our projective geometry video lectures. We are dealing with conics currently, and this time I want to do a little recap of things we already had in the Geometriekalküle lecture. I want to show you how to derive the matrix of a conic that passes through 5 given points. And I want to do it in two different ways. I want to do it in an algebraic manner and in one that is more geometrically motivated. So let's start with the algebraic considerations. So assume you are given 5 points in reasonably general position. So for the moment assume that you have 5 points such that no 3 of them are collinear. And now you're looking for a conic that simultaneously passes through all these 5 points. In other words, if you take the homogeneous coordinates of your 5 points, you are looking for parameters a, b, c, d, e, and f such that your conic equation is simultaneously satisfied for each of your points. This, in a straightforward manner, leads to a system of linear equations where you have 5 times 6 matrix here, where each row is occupied by the squared coordinates of your points, and every solution here makes sure that you simultaneously satisfy the conic equations for all your 5 points, and so you derive the coordinates of your conics. So, this is a very general approach, but you know we are always searching for geometric insight. And I want to give you a kind of more insightful solution of what's going on here. And I would call this more a kind of geometric solution. So assume you are given 5 points, again in general position, no 3 of them should be collinear. And as a first step, you focus on the first 4 points here and consider 2 degenerate conics passing through these 4 points. So if you do so, so here you have a green conic that is decomposed into the lines AC and BD, and you have a purple conic decomposed in these other 2 lines, and you can write down the equations of these conics just in a straightforward manner. So just multiply 2 determinants, each of them involving your point P, and set this to be 0. What does this mean? Well, this expression here can only become 0 if one of the factors becomes 0, which means that either P is on the line AC or that P is on the line BD, which exactly describes your degenerate conic. Similarly, for the other degenerate conic, you get this equation. Observe that P is involved here as well. As a next step, we consider the set of all conics passing through A, B, C, and D, and you simply get that by a linear combination of your 2 factors we had here. So if you write down an equation, lambda times one of the expressions plus mu times the other of the expressions, and set this to be 0, then you described a general conic through your first 4 points. Why is this the case? So first of all, it is again an equation of a conic because you made the linear combination of 2 quadratic forms. And secondly, it passes through A up to D because if you, for instance, look at point A, for point A, both the purple expression and the green expression both become 0, so any linear combination has to be 0 as well. So what you get here is a conic through your 4 points, and as a matter of fact, it's not too difficult to prove that every conic through those 4 points has to be of that shape. So now our next task is to take this solution. So it generally describes some conic through your 4 points. And now we have to do kind of curve fitting. We have to make sure that this solution here also passes through point E. And this can be done by choosing very specific numbers for the parameters mu and lambda. And I give you the solution right away. So the parameters you have to choose is you have to choose this here for lambda and this here for mu. So why is this the case? So look what I've taken here. The expression up here is essentially an expression that involves point E, and it is derived by taking the green expression here and replacing E for P. And similarly, this expression here is derived by this one over there and exchanging P for E with the effect, well, it's still a conic through A to D. And if you plug in point E as your point P here, then this expression is exactly the same as the other one, so it will also evaluate to 0. So for this specific choice, you get a conic through all 5 points. And well, now you may ask how to get our matrix from that. Essentially, it's very straightforward. So all the parts of these equations we have are directly derived from our data of the 4 points. So actually this and this here can be written as a matrix equation, and these two factors are simply numbers that you can calculate from your 5 points. So all in all, you get a quadratic form, and you can symmetrize it by the usual trick of replacing the matrix you get here by summing it to its own transpose. So you take the usual symmetrization step. So this was one way of getting conic through 5 points. And as a next thing, I want to rewrite this expression a little bit in order to get even a little bit more insight. So I took this expression here and shuffled one of the terms to the other side of the equation, and then by dividing I sorted everything that contains an E and everything that contains a P on both sides. So what I get after that is this equation here, which tells you that implicitly your point P lies on this conic. So say you have a point P also lying on that conic. If this equation here is satisfied, and if you look closely, you will observe these are nothing else as cross ratios of the points A, B, C, D seen from point E and seen from point P. And the reason I write that down is that we will need this formula, this characterization of conics later on in many contexts. So let me restate it once more. 6 points are on a conic if and only if 2 of these points, in our case it's E and P, see the other 4 under the same cross ratio. So this is a very nice characterization of 6 points being on a conic, and it gives us a nice relation of conics, points on a conic, and cross ratios that is, I would say, very insightful. You can think of it even in a different way. So fix a conic, fix 4 points on that conic, then any other point sees these 4 points under the same cross ratio. So the cross ratio is an invariant of the conic and the 4 points on the conic. So let me close this video lecture with a little animation of a conic determined by 5 points, just that you once have seen how things behave. So you see how you can get smoothly from an ellipse to an hyperbola, how the hyperbola changes branches, how you get degenerate situations when 3 of the points are collinear, and how actually for 4 fixed points you end up with 3 types of degenerate situations. Let me show you that here in a moment. So let's take this point. You have one degenerate situation here, you have a second situation here, and there is a third degenerate situation over here. Also, this will be of importance later on. In our next slots about conics, we will deal with the important concept of polarity and duality with respect to a conic. See you there.